there's some
Definitely can attest to that.
Yeah.
I took it in spring and I didn't turn out too well.
With Alex?
No, not with Alex, with Eldon.
Eldon, I see. Yeah, it's either a little bit
I passed the lab.
I see.
Not too bad, I guess.
What side are you going to be on today? What side are you going to be on today?
That's a good question. I think I tend to be on. Yeah, I really don't know. I'll try to be on this side. I think more people are like sitting over here. Remind me of your name again?
Rona.
Rona. Okay, I got it. And by the way, your name again?
I'm Mitchell.
Oh, Mitchell. I see.
Are the workbooks graded on accuracy? Like best accuracy?
Yeah, I'll go with that in 1 second. So, question about workbook. So workbook will be graded. No, the first workbook is only on completion. All the future workbooks will be on a mix of correctness and completion. Roughly half question by completion. When you show your work and then put down a sincere amount of effort, you get full points. The other half of the questions will be graded by accuracy. But we do give a lot of partial credits. Right. So really the goal for this workbook is to have a lot of like low weight assignments for you to learn and then get the feedback, learning feedback happen. Try it out, then check out our solution, see how we think about the problem, and if there's a more effective way of solving the problems. And eventually you have like a major milestone at the midterm and the final exam. Right? All of this work is just to help you get ready for those major milestones, and in the meantime, make this learning happen. So here's our today's agenda. We're going to talk about error detection and correction techniques in binary. Right? Transmission error happens. Communication channel could be hijacked by some attacker. We need to make sure that reliable communication and storage happens for binary numbers. And I'll give you an introduction to Boolean algebra. That is really the transition between number theory and circuit design. All right. Starting with error detection and correction code. Okay, I'm going to switch my presentation to the tablet. Yeah, any questions about any logistical stuff? Right. Perfect. Okay, now we're going to continue with error detection and correction. I hope you still remember my credit card number. That would be a very nice extra credit question on the midterm. I'm just kidding. Error detection and correction is everywhere. We have that in the credit card number. The last bit, the last digit is a checksum digit, which allows you to capture 1-bit errors. And QR code is also embedded with some error correction features. It's not perfect error correction. It cannot correct any error. But for some of the smaller errors, it can generally correct them and tolerate it really well. So this credit card, they have this 1 additional digit at the end. And the way it is computed is using this Loon algorithm. The idea is, credit card numbers are in general 16 bits, except for that crazy American Express, which has only 15 bits in the credit card number. In general, it is 16 digits. So the first 15 digits are the numbers. The last digit is a checksum digit. And what they did is they double every other digit in the original credit card number, and then they take the summation of all the digits. So this will represent essentially doubling of every digit sitting at the this position, every other position. And then we take the sum of every digit. So 1, 0 is treated as 2 separate digits, added up to 1. Right? 1, 6 are treated as 2 separate digits, added up to 7. And they want to make sure that eventually, when you add up all these digits from the number together with the checksum bit, you have a multiple of 10. And that is the goal. Right? In other words, to calculate that checksum bit from the card number, you take the summation of some of these doubling weights and all the digits, and subtract this number from the nearest multiple of 10. Right? So you get 59 from all the numbers, so you need to add down 2 to the checksum digit to make sure that overall the sum is a multiple of 10. And this allows you to catch some common input errors. So you see the reason why we're doubling some of these digits. That depends on how the error occurs. A very common error for credit card number is you transpose 2 digits. You flip the order of 2 adjacent digits. And to catch that error, they need to have these alternating weights. Right? And they can also detect a single bit error and also duplicate of a digit. So what this tells us really are the principles for designing error detection and correction codes. We first need to figure out how error occurs, and then design the correction and detection scheme according to that error behavior. Right? For credit cards, people have done some profiling and they found out transposition is a common error. For binary number, we also need to define in which way error occurs, and then design error correction and detection scheme according to that error pattern. And once we have modeled the errors, we want to define a set of valid codes and a set of invalid codes. Right? Anything that adds up to a multiple of 10 is valid. Anything else is invalid. We need to make this definition to be able to differentiate what is good and what is not good. All right, and we're going to just bring these same principles to designing error detection and correction scheme for binary numbers. And error happens for binary transmission. So suppose Alice sent a message to Bob saying that my dad owns a food truck, which is very cool. It's one of my dreams when I was a kid to have a food truck. But if there's a 1-bit error happen, that could flip 1 bit over here. And now when Bob interprets the message, the 4 letters FOOD becomes GOOD. So the message overall becomes my dad owns a good truck, which is still good, but it's not as cool as having a food truck. It's more like showing off. So how do we deal with it? Well, one thing Alice can do is to add on 1 extra bit, right? 1 extra bit on top of the original message. And this extra bit will be 0 if the original message has an odd number of ones, even number of ones. It will be 1 if the message has an odd number of ones. Right? An odd and even parity bit depending on how many ones you have in the original message. And let's say now when Alice sends this new message, the elongated message to Bob, Bob can verify if that additional bit makes any sense. Right? So Bob will calculate, well, how many ones do I have in the message? As it turns out, under this 1-bit error, there will be an odd number of ones instead of the original even number of ones in the message. So that additional parity bit no longer makes sense. That's how Bob is able to tell that something has gone wrong, either during communication or during storage for whatever reason. And when Bob detects an error, he can ask Alice to send him the message 1 more time. With this additional bit, we can essentially differentiate 2 different scenarios. Is it correct or is it flipped? Right. Any questions so far? Right. And this is assuming that the communication channel, the error model over there, will be a 1-bit flip. Right. Based on that 1-bit flip pattern, we add 1 additional bit to check the parity of ones in the original message. All right. So remember I told you about this 2 out of 5 code. That's one of the ways to encode decimal digits. We have 8421, binary coded decimal, XS3, grid code, etc. And one of them is 2 out of 5. And 2 out of 5 is also a kind of error detection code. So let's say again, Alice wants to send a number to Bob, number 0. So she looks up in the table, finds out the encoding for number 0, which is 00111, and she sends it to Bob. And if there's a 1-bit error happens during the communication, Bob might receive this number, 00111. And obviously, this number is not one of the valid numbers in that coding scheme. Right? Again, now we can differentiate valid numbers and invalid numbers by looking for the number of ones. It has to be exactly 2 out of 5 for the number to be valid. And we have 3 ones, that is not a valid code. So again, he can tell that the data is wrong, but he cannot quite recover the original data. Because this could come from that message with a 1-bit flip in the middle. This could also come from, let's say, number 1 with a 1-bit flip on the 2nd position from the right. Right? It could also come from number 2 with a 1-bit flip on the last position. Right? So many valid codes under a 1-bit error could give you this message. So he cannot quite do error correction. Detection, 1-bit error detection, perfectly fine. Error correction, not quite feasible yet. And what allows this 2 out of 5 code to deliver the error detection capability is its Hamming distance among the valid code words. These are all the valid numbers. And what I mean by Hamming distance is the number of bit positions that differ between two binary strings. So when you look at any two valid code words from this table, right, any two of them, they differ by at least 2 bits. Right? Let's say these two, they differ by 2 bits. Right? These two, they differ by 2 bits. These two, they differ by 2 bits. Any pair, they differ by at least 2 bits. What that means is that if you send me a valid message, and there's a 1-bit error happens, this 1-bit error is not powerful enough to take you from one valid code to another valid code, because the two valid codes always differ by at least 2 bits. Right? That's what allows for error detection. The distance between any two valid code words is greater than the power of this error. Right? And when that minimal Hamming distance among all the valid code words is 2, you can make 1-bit error detection. But if you have a 2-bit error, right, it's possible that you send me this message and I receive this message. Right? They differ by 2 bits. So 2-bit errors, you cannot quite handle it using 2 out of 5 code. Right? In other words, you can really analyze the error detection and correction capability by looking for the minimal Hamming distance among any pair of valid code words. Any questions so far? Any questions? All right. What I was showing you earlier, right, to append one additional bit at the end, this idea is really formally called parity code. And for parity code, someone has an n-bit message. They'll compute a parity bit using the XOR operation. XOR operation is defined by this circle with a plus sign in the middle. That is a parity generator, which means this operation will produce a 1 when you have an odd number of 1s in your original inputs. Output a 1 when odd number of inputs are 1s. So for any 4-bit message, or actually n-bit message, we can append in one additional parity bit depending on the number of 1s in the original number. Like the single 1, I put down a 1, 2 1s, I put down 0. And what this will ensure is that eventually we'll look at this full 5-bit message, including the original message and the additional parity bits. It will always contain an even number of 1s. If the original message has an odd number of 1s, like here, overall, after adding the parity bits, we have an even number of 1s. Over here, original message, odd number of 1s. After parity bits, even number of 1s. Original number, even number of 1s. After parity, still even number of 1s. All of these 5-bit messages, including the parity bits, will have an even number of 1s. That's what this parity code, this additional parity bit offers us. And that is really the invariant property of valid code words. For any valid codes, they will have an even number of 1s, including all the message bits and the parity bits. Right? If you look at this total 5-bit message, you will always have an even number of 1s if it is correct. But for any 1-bit error, it's going to flip one of the bits, right, which will make the total number of 1s an odd number. And therefore, whenever you see an odd number of 1s together, you can tell that there's an error. Right? Again, we're assuming that only 1-bit error has happened during communication. And that's actually the reason why we only insert 1 parity bit, to be able to differentiate between 2 scenarios, error with 1-bit error, and error-free. And a different way you can look at it is, when the receiver receives the 5-bit message, he can recompute the parity bits based on the 4-bit message and see if that recomputed parity bit matches the one that he received. So for example, when the receiver sees this message, 1001, he can recompute the parity bits, which will be a 0, right? Even number of 1s, XOR parity counter will give you a 0 output, and 0 does not match the 1 parity received. That indicates an error. So that's essentially everything about error detection code. 2 out of 5 has the invariant of having 2 1s out of the 5 bits. Right? This parity code has the invariant property of having an even number of ones in total, or this one, when going through that XOR parity operation, should give you a matching parity bits, right? Those are the invariants for the valid code words. And when one bit error happens, it will violate the invariant, so we can tell that apart. Yeah. Any questions? All right. That's about error detection. And then let's move on to error correction. Right? Correction is a little bit more stringent than error detection. Right? For detection, you only need to tell whether it's error-free or error impacted. For correction, you need to be able to pinpoint exactly where the error happens and be able to flip back the binary bit to the correct number. Right? So there are a lot more scenarios and information you need to capture with some additional parity bits. So let's say, again, we're trying to send a 4-bit message to the receiver. Right? And error could really happen on any of those bits. So there are already at least 4 scenarios you need to be able to differentiate. Right? Whether error happens at M0, or M1, or M2, or M3. They need to be eventually represented in different ways. And to represent these 4 scenarios, you need at least 2 bits of additional information to be able to differentiate the 4 cases. Right? Just in terms of information theory, to represent 4 different scenarios, you need 2 bits of information. Right? So therefore, we can append 2 additional parity bits to that 4-bit message. But this is not quite enough. And this is not enough for 2 reasons. Number 1, we still need to reserve one representation to indicate the error-free case. Right? That's another scenario we need to be able to represent. And that's the first reason. There's one additional case for that no error situation. And secondly, right, when you add these additional parity bits to your message, you need to send the full 7-bit message to the receiver. So error could also happen on the parity bits. Right? As you're adding more bits to your message to handle error detection and correction, these additional bits are also subject to error. So those are some additional scenarios you need to be able to tell. Right? Error could also happen on one of these parity bits, P0, P1, or P2. But if you look at this total number of scenarios, all the different cases, I need to be able to differentiate and represent. There are 8 of them in total, and that fits exactly into the expressive power of 3-bit binary numbers. 3-bit number, there are 8 different value combinations, and that's exactly enough. If you construct things in a very optimal way, that's exactly enough to differentiate among these 8 cases. Right? So everything just adds up together pretty well. Adding up 3 bits, you just have enough expressive power to cover message error, parity 1-bit error, and to represent that no error scenario. Yes?
So the error is if there's an odd number.
The error is 1-bit flip. One of these 7 bits getting flipped. They can be flipped from 0 to 1 or 1 to 0. Flip could happen in both directions. But think about you're sending me a 7-bit message, and one of the bits gets flipped. That is the error model. And among these 7 bits, 4 of them will be message bits, 3 of them will be these added parity bits to embed some of those invariant properties. And when I receive the 7 bits, I can analyze the 7-bit message to figure out whether 1-bit error has happened, or if that has happened, on which position the error happened. Yes?
Can you explain one more time what does the parity bits represent?
So parity bits, in general, parity bits means some additional bits you use to embed some invariants. For the this kind of single parity bits for error detection, right? That's like an odd even counter for the number ones in the original message. But in general, parity bits can be defined in any way you like, but they have to be related to the message bits. And we'll see one particular construction in 1 second, how to place the message and parity bits in a particular order, how to evaluate the parity bits in a specific way, so that we can optimally represent those 8 different scenarios and be able to do error detection and correction. Yes?
So going back to the other slide, the 7.
Yes.
So
you can tell if there's an error if the parity bit doesn't match. Like if P0 has like a 1, and then M1 had even ones, then you can tell that's an error.
Yeah, something of that sort, depending on how these parity bits are calculated in the first place.
Oh.
Right? So here I'm defining a particular way of computing the parity bits. Parity is the XOR of all the message bits. This is one definition of constructing parity code. Right? You can define it in a different way, and we will define it in a different way because we have like 3 parity bits, and we don't want them to all cover the same message bits. And by using different parity bits to cover different message bits, we're able to kind of have different this kind of equation together when you evaluate parity together with message through a new expression, and then that will allow you to get different values out of this expression, right? The eventual correction equation to be able to pinpoint the error.
And is it the last part? Does it always sum to 0, or is it just in this case?
It's only in this case, right? It's only for the 1-bit parity error detection code. So this equation, you can call this the parity equation, right? We're trying to embed some additional invariant into the message. This one, you can call this a correction equation. So the sender will calculate parity bits, include the parity bits together with the message. The receiver, when I receive your 5-bit message in this case, right, I'm going to run through a different set of equations to get some binary result. And that binary result indicates why the error has happened, or for the error correction code, where the error has happened. And we need to define these 2 equations for any coding scheme. All right. So coming back over here, this is saying that in the most optimal construction, you need 3 parity bits to correct an error, a single-bit error, for a 4-bit message. And now we're going to see how we can put them together and then build those equations. Yeah, another one of these general formula. Right? So suppose you have an n-bit message, and you want to add some additional C parity bits, right? Like 4 and 3 respectively, from that previous example. So you have 4-bit message. And you want to add 3 additional parity bits. You want to make sure that when there's a 1-bit error, the error could happen at one of these message bits, one of these parity bits, and you need to reserve one representation for the error-free scenario. Those are all the different scenarios you need to be able to represent by these additional parity bits. Because the message can really be anything, and they do not have any invariant, and all of these invariants are embedded externally through parity bits. And 2 to the number of C's, with 2 to the number of 3, those are all the different scenarios that could be encapsulated by 3 additional bits. Right? To make sure that one is greater than or equal to all the 1-bit error conditions and no error condition. Right? So this equation has to be true. So for instance, let's say you have a 4, you have the resource for 4 parity bits. Right? Then we want to make sure that 2 to the 4 is greater than or equal to the number of message bits together with 4 parity bits and 1 condition for the no error case. So how many message bits can I handle with 4 parity bits? That would be 16 minus 4 minus 1, which is 11. So if you have an 11-bit message, you can put down 4 parity bits and construct an error correction code. 4 parity bits just gives you enough expressive power to differentiate among 16 different cases. Right. 11 for 1-bit error on the message, 4 for 1-bit error on the parity, and 1 scenario for the error-free case. All right, but we're going to spend the vast majority of our time on this 4-bit message and 3-bit parity. All right, and this code is invented by Richard Hamming. Have you heard about this guy? From where?
Oh, sure. His name is really familiar.
Yeah, Hamming, whatever is, just all over the place. And many things related to computer science, math, graph theory, and they're all under his name. Could anyone name some terminologies like Hamming, whatever? which is a Hamming distance, right? The number of bit differences between two binary strings. Anything else under his name? Hamming code, that's very nice. That's what we're about to see for error detection. Sorry, error correction. And Hamming won the Turing Award for his work on numerical methods, automatic coding systems, and error detecting and error correcting codes. So what we're about to see is essentially 1/3 of a Turing Award, right? His error detection and correction code. That is 1/3 of the Turing Award. And he worked at Bell Labs. Bell Labs is really the driving force for many innovations in electronic designs about like 40 years ago. Since 1950s until like up to 1970s, or maybe 1940s to 1970s, many of the innovations, ways we design circuits, we optimize circuits, they all come from Bell Labs. And we're gonna see, I would say, 5 more people from Bell Labs in the next 4 weeks. When we learn about combinational design, sequential design, many of these methodologies are developed by people from Bell Labs. All right. So Hamming probably took our equation, 2 to the n greater than or equal to n plus c plus 1, and then he found out that 4 parity bits is enough to do error correction for 4-bit message. And he essentially extended the idea of parity codes. The way it works is as follows. For a regular 1-bit parity code, it covers all the message bits. Right? All of the message going through an XOR expression gives you the parity value. But since we have 3 parity bits, we can use them to cover different message bits. Right? We only use P0 to cover these 3 message bits. So they sort of form into their own error detection group. And we use P1 to cover M0, M1, M3. I have these like underscores. Right? They represent the coverage of parity bits with respect to the message bits. Parity bits are put at those kind of weird positions, and they cover different message bits. And finally, P2 covers M0, M2, and M3. Just like our regular parity code, but now we're using different parity bits for different message bits. And this information combined, as you'll see in 1 second, allows us to exactly pinpoint where the error happens. Right. So formally speaking, that's how we compute the parity equation. P0 depends on the first 3 message bits, M0, M1, and M2. Right? P1 depends on M0, M1, M3. P2 depends on M0, M2, M3. And that's represented by that equation. I never remember that equation. I just always try to look at this table and then visually figure out which parity covers which message. I think it's also a lot easier when you want to run some binary calculation to have this kind of visual aid. So let's say Alice again wants to send a message 0010 to Bob, right? And this is what Bob received. So before Alice sends a message, she computes the parity bits. 001, odd number of ones, so we put the 1 over here. 000, even number of ones, no one, it's like 0, 1 is like an even number. So we put down a 0 over here. And then finally for P2, 010, odd number of ones, we put a 1. That's how she can expand the 4-bit message into this 7-bit message with 3 additional parity bits. And when Bob received it, again, assume that 1-bit error has happened. So how do we typically deal with it? We just check if those parity bits make any sense, right? And we have 3 parity bits. What we can do is we can see if each of them makes sense. So let's verify this P0. So P0 covers these 3 bits. Right? So 0, 1, 1, I have an even number of ones. So I should have a parity of 0. Right? If the message is correct, I have 0, 1, 1 over here. This bit should be 0 because I have an even number of ones. So I know that P0 doesn't make sense. Again, this is a simple extension of the parity code, right? But now we're just focusing on only 3 of the message bits and 1 parity bit because they sort of form into a group. Right? And then let's check the second parity bits. Right? Between P1 is M0, M1, M3, M0, M1, and M3. 0, 1, 0. We have an odd number of ones. So this bit should be a 1. Right? parity for 0, 1, 0, that's an odd number, so this bit should be a 1. So we know that P1 also doesn't make sense. Right, finally, when it comes to P2, 0, 1, 0 should give you a 1. Right? P2 is kind of fine, right? 0, 1, 0 gives you a 1. So P2 is fine. Right? P2 has not been impacted by the error. And let's see, okay, now the question is, what is the 1-bit error that could justify those observations? So when you look at the P2's equation, right, P2 is fine, which means all of these bits are correct. If you have a 1-bit error at any of these bits, P2 will be flipped. But P2 is fine. Or P2 still makes sense, which means these bits are correct. They have not been impacted by a 1-bit error. Right? Just think of this as like a small parity code only for those 3 message bits. And because that makes sense, we know that all of these message bits, together with the parity bit, are correct. So what else can we tell? So we know that there's a 1-bit error, right? Because some of them do not make sense. And this 1-bit error affects both P0 and P1. The 1-bit error affects both P0 and P1. And whether you want to look at it through the equation or in this visual way, what is the 1 bit that can affect both P0, the blue line, and P1, the green line? What is the 1-bit error that can affect both? Yeah, Rona said M1. That's exactly right. M1, you see there's an underscore. For P0, it goes into P0 equation, right? It goes into P1's equation. So M1 is the only error possibility that can explain the invalid P0 and the invalid P1. And that must be the position where I have the error. And that's exactly right. That's when the 1-bit flip happens. So essentially, what we do over here is we check if each and every parity bit makes sense. If they don't make sense, we sort of represent that as a binary number. We just flag it as a 1. If it makes sense, we flag it as a 0. And then when you read out that binary number, that gives you position 6. Position 6, according to that table, is M1. M1 is the one that can justify the invalid P0 and the invalid P1. So M1 is impacted. M1 affects both P0 and P1. M1 affects both P0 and P1. And then you sort of convert this validity check result into a binary number that will give you the position. And the way actually originally, right, the way we order them in this very weird way, and the way we specify those parity equations, is to make sure that eventually we can use a binary rating to indicate the error position. And we'll see that in a second. Does it make sense so far? Right? The idea of having parity bits to cover different message bits, and eventually collect all this intelligence and be able to find out one error that can explain all these mismatches. And that will tell you where the error happens. Again, if you look at that table, right on top left, every message bit is covered by a different set of parity bits. Right? So they will affect different parity bits. And this differentiation is what allows us to make error correction. Right? Every bit error will produce different validity results on those parity bits. Yes?
I have a question. So what do you think the parity bit is the one that was the error?
Yes. So let's say if the parity bit is the one that goes wrong. Parity bit is sort of covered by itself. Right? So if you only have a parity bit error at P2, then P2, of course, does not make sense. And everything else will make sense, because the other parity bits depend on only the message. Right? So you get something like 001. P2 is erroneous. P0 and P1 are correct. And you see, according to the table, P2 sort of covers itself. And it is put at position 1. You see, parity bits are put at position 1, position 2, position 4, exactly for the reason you raised. So that when you have a parity error, then that binary number will have a single 1, 1 or 2 or 4, to indicate the parity position. So let's, okay, I'll show you this example. So again, same message. So let's say parity, the error happens at this position, right? P2 position. So I would get 0, 0, 1, 1, 0, 0, and 0. And then if you check for P0, P1, P2, P0 makes sense. 0, 0, 1 gives you a 1. P1, 0, 0, 0 gives you 0. P1 is, makes sense. P2, 0, 1, 0, 0 does not make sense. Right? I have an odd number of ones, but P2 is a 0. So I would sort of describe that condition as 0, 0, 1. Right? P0, P1 makes sense. P2 does not make sense. And 0, 0, 1, when you look at it, it's a binary number that indicates position 1. So exactly P2. Right? Whenever you have a message error, like a 1-bit error on the message, it will impact at least 2 of the parity bits. But if the error happens on the parity bit, it will only impact that parity bit by itself. And parity bits are positioned at this position 1, position 2, position 4, so that that binary number still indicates the error position. Yeah. Anyone got any questions? I think this is a pretty cute idea. You know, if you go back like 70 years, do you think you can come up with this idea with the knowledge you gain from parity codes and 2 out of 5? I mean, if you do, you can win a Turing Award. That would be super impressive. Right? It's not a complicated idea. Right? This is I would say a straightforward extension to the parity codes. But to be able to realize it in the first place without any prior knowledge, that probably takes some hard working.
Do you think you can do it?
I don't think so. Yeah, but if you look back into the 1950s, digital circuits were barely a thing. There's no transistorized computers yet. Right? There's no integrated circuits, and there's barely any communication happening in binary. So you have to a little bit look forward to see what is the next technology coming up in another 10, 20, 50 years to be able to just dedicate yourself to this problem and then develop all the mathematical models to eventually arrive at such an elegant solution. Yes?
I'm just curious. So I noticed that it's only 7 bits. So like, how would you actually apply that? Because you would normally do like, in terms of power to 2. So like, and this is 7 bits. So like, how would you actually use that?
Could you repeat the question?
Because I believe it's just to make sure, like, it's like sending a message.
Yeah.
But it's not in a power of 2. Is there anything that you need to do for it? Or can you just...
Okay, so you're probably thinking about, let's say, if like every word is defined as an 8-bit, and how could you send a 7-bit message from it? So you could say that you can use 7 out of the 8-bit positions. You don't have to use your full bandwidth. Yeah, you have to essentially only use 7 bits out of the 8 bits. So that because three parity bits can only cover 4 message bits. If you put 5 message bits, you cannot guarantee 1-bit error correction. So in general, when you add additional parity bits, you are losing a little bit of the expressive power of the numbers. You have to reserve some invalid code numbers. Anything that does not satisfy this property, those are invalid numbers. And we have a huge amount of invalid numbers. Essentially, within a 7-bit bandwidth, we can only send a 4-bit message. And that's kind of the optimality that we have to tolerate to get this error correction and detection benefits. Right? Again, to make the distinction between what is correct and what is incorrect. You cannot fully make use of your bandwidth. All right. So to recap this procedure, Alice wants to send a 4-bit message to Bob. So she will first compute 3 parity bits according to that table or according to those equations, and then send this full 7-bit message to Bob. Bob, on the other hand, will compare the parity bits with the message bits that each parity bit covers. And formally speaking, you can run everything through an XOR expression. Parity XOR the message. And in fact, if they match, this one will always be a 0. If they do not match, this number will show up as a 1. And eventually, You read out this number, the correction code C0, C1, C2 as a binary number. And if it's all 0, then nothing has gone wrong. It's perfectly correct. If it's non-zero, then this number will indicate the error position. All right. So I have an exercise for you to try it out. Assuming you're the receiver and you receive this message, right? Could you figure out where the error happened and then recover the correct 4-bit message for me? I'll give you a minute to work on this exercise, right? Either through visually looking at the table or, mathematically through the equation, whichever way you like. Again, I, as a receiver, the only thing I see is the 7-bit message, right? But I know they should have been generated according to the Hamming code equations. So I can just kind of reverse engineer that equation, figure out which one is invalid, to find out if error has happened and where the error has happened, if any. Yeah. Anyone got the number? Got the number.
You just changed the first bit to a 1.
The first from which side?
From the left.
First from the left. So I think the error happens over here. Yeah. I'll take that as a candidate, and then we'll see if that's correct. Michael, you got your answer.
I think P1 got flipped.
P1. So you're using this position. Right, the second one from the right has the error. Eric, you got an answer? Not yet.
Oh, me. Oh, sorry. So I actually have a question for C0, C1, C2. Wait, what are those stands for? I'm a little confused.
So C0, C1, C2 is kind of the comparison result.
Yeah.
If it's valid, if P0 is valid, C0 will be 0. If P0 is invalid, C0 will be 1.
Okay.
And that's just how formally we represent it. If P0 matches whatever on the right, M0, XOR M1, XOR M2, if they match,
I see.
right, that XOR will give you a 0 output.
I see. But can P0 and P1, P2, can they ever be wrong? Or?
They could also be wrong.
Oh, I see.
If they are the only bit that is wrong, you see only one of the C bits will be affected. Right? And that would indicate position 1 or 2 or 4 in binary number. Those have a single 1.
Wait, so can you repeat that? So if P0, P1, P2, if one is wrong, that means only one of the above correction equation is wrong. Or
Yes. If one of the parity bits is wrong, you see message bits, they go into multiple equations.
Okay.
Right? So if one of the message bits is wrong, we'll have multiple ones in those C bits.
Okay.
If parity bit is wrong, only one of the C bits will be affected.
Oh, I see.
All right. Let's come back and let's do it together. So again, I want to check if P0 makes sense by seeing if these 4 bits together make sense. Right? And these 4 together, they do not quite make sense. So C0 equals 1. Right? Equation-wise, 0, XOR 0, XOR 1, XOR 0, you have an odd number of ones, so C0 is 1. Or you could say that P0 does not match the expected parity value from these 3 bits. And then the next line, 0, 0, 0, 1. Again, C1 would be a 1, which means P1 doesn't make sense. All right, finally, this bit, this bit, this bit, this bit together gives you C2 equals 1, which means P2 doesn't make sense. So this tells us, well, error happens at position 7. Essentially, the message bit that affects all 3 parity bits. So that is position 7. So I know M0 is wrong. We're not done yet. Right? This is only to find out where the error has happened. You still need to make the correction and recover the original 4-bit message. That's what the receiver is trying to receive. So what we do is we can flip this number 1 0 1 0 0 1 0, flipping the first number, and then extract out the 4-bit message from the 7-bit code. So the 4-bit message will be this 3-bit together with this bit. So the message should be 1 0 1 0.
Can you repeat that sentence again?
Yes. So once we found out the error position, we're not done yet. We need to make the correction. And in binary, since this is a 1-bit flip, the correction will just happen by flipping back 0 to 1 or 1 to 0. Right? Error position, there's only one kind of correction you can do to flip it. And then once you flip it, you get essentially a consistent 7-bit message. But only 4 of the 7 bits are message bits. And you need to extract out those 4 message bits. And that's what you're really trying to receive. Right? Those message bits sit at position 7, 6, 5, and 3. 7, 6, 5, skip 4, and 3. Right? So those 4 bits together, you took them out. That gives you 1 0 1 0. Yes.
Why is C1 equal to 1?
Why is C1 equal to a 1? C1 is P1 and 0, the one with a green underscore. So 0, 0, skip these 2, 0, 1. And this 1 would not be a valid parity code for 0, 0, 0. So C1 or P1 doesn't make sense. So you represent it as C1 equals 1.
So you put 1 if it doesn't make sense?
So this is what I received. I'm trying to verify if P1 makes sense by comparing it with the original 3 message bits that this should be computed upon. And this one will be computed upon 0, 0, and 0. And if there's no error, there should be a 0. Right? But 0, 0, 0, you have a 1 over here, which means they don't quite match up.
Yeah.
So either the parity bit is wrong or some of this message bit is wrong. And you represent it as a flag of 1.
Okay.
And eventually this can be read out as a binary number to indicate error position. Any other questions? All right. So now let's just come back to answer this question. Why is Hamming code ordered like this? Right? Why did we follow this order? Well, we follow this order because we want that correction code, C0, C1, C2, to be interpreted as a binary number and converted to a decimal to indicate the error position. So whenever an error happens at M0, I want all 3 correction equations to be affected. So this bit at position 7 needs to be covered by all the parity bits. And that can be regarded as writing out those positions as a binary number. 7 is 1, 1, 1, 6 is 1, 1, 0, and whenever you see a 1, you cover the bit with the respective parity bits. And we know that we want to make sure that this parity error happens at position 4, position 2, position 1. So once you find out this relationship, parity will be computed based on the rest of the message bits. Again, these positions are derived from the binary representation for those positions, so that eventually, after someone has calculated the correction code, they can read it as a binary number to reverse engineer the positions. right? This is how I also visually remember, this parity equation. I never really remember the equations, but I know what are their positions. This just is, use 4 and then skip all the remaining. Use 2, skip 2, use 2. 1 skip, 1 skip, 1 skip. And that exactly corresponds to the binary representation for those positions. Whenever you see a 1, you include that in the respective parity and correction equations. So again, coming back to this idea of Hamming distance. If the minimum Hamming distance between any two valid code words, think of 2 out of 5, right? Minimum Hamming distance is 2, you can make 1-bit error detection. Essentially, unless this error is capable enough to reach from one valid code to another valid code, you can always detect it. So if the minimum Hamming distance is n, you can do error detection for n minus 1-bit error. If you want to do error correction, again, right, it's like a more difficult job. And you have to make sure that this error has not reached halfway between two valid codes. What I mean by that is, think of a scenario where two valid code words differ by like 3 binary bits. And if you have a 1-bit error, right, you go from here slightly into this invalid region, then you can recover it by bringing it back to the nearest neighbor. Right? Again, forget about those exact binary equations, just conceptually think about this problem. When you have a 1-bit error, and then you find out, well, this one has a very close neighbor that is valid, I can just recover it back. But when you have a 2-bit error, you can no longer recover it to the nearest neighbor to get the original message. It's getting too close to another valid code word. Right? So you want to make sure that the error is not strong enough to take you more than halfway. So this is really saying less than n divided by 2. Right? If you don't want to remember this complex formula, this is really just smaller than n divided by 2. Right? Less than halfway between two valid code words. And if we look back into this Hamming code construction, right? And we're trying to figure out what is the minimum Hamming distance between two valid numbers. Well, we need to first try out some of those messages. So let's say 0, 0. So let's say I want to see what is the distance between these two numbers. Right, 0, 0, 0, 0, 0, 0, 1 as messages, and they're very close to each other. I want to calculate, after I have expanded them with parity bits, what is the resulting overall Hamming distance. Right? So just do the computation real fast. So this will be 0, 0, 0. This will be 0, 1, and 1. Right? After following the parity equations. And these two numbers differ by 3 bits. Right? Eventually, when you try all the combinations, the minimum distance is 3. You're guaranteed to have a minimum of 3-bit flips between two numbers. And that kind of makes sense from the parity equations. If you think about flipping just one of the message bits, right, it's going to impact at least 2 parity bits. Right? No matter which message bit you flip, it's going to impact 2 parity bits. So if the message differs by 1 position, the parity will differ by at least 2 positions to give you the minimum Hamming distance of 3. And that is what allows for 1-bit error correction. HD of 3 allows you to correct 1-bit error by bringing it back into the nearest neighbor, right? Flipping 1 bit back to recover the correct message. And let's say if your messages differ by 2 bits. So let's say 0, 0, 1, 1. Right? Again, I'll do this calculation. This is a 1, this is a 1, this is a 0. Right? This differs with the original message by 4 bits. Right? Again, it is at least 3. It could be 4. I think 4 is probably the maximum. But it is always greater than 3, no matter which combination, which pair of message you try. Again, that is connected to this formula. When the minimum Hamming distance is 3, you can actually detect 2-bit errors and correct 1-bit error. The other thing you can do is you don't have to construct this parity bits following a particular algorithm, you can just arbitrarily define a set of valid numbers and claim those are the only valid codes, and anything that do not belong to that set are called invalid. Right, so let's say you have a 10-bit code. You're declaring these 4 10-bit numbers to be the only valid numbers. That's perfectly fine. We just share with each other a dictionary and then point out these numbers to be the only valid choices. And whenever the number I received does not match any of them, that is an invalid number. And again, you can analyze its error detection and correction capability by finding out the minimum Hamming distance. So what do you think is the minimum Hamming distance between any pair of these 4 numbers? Yeah, what is the minimum Hamming distance? Right, so well, formally speaking, we need to check every pair. Right, so these 2 pairs differ by a HD of 5. These 2 is HD of 5. These 2 HD of 10. These 2 is 10. These 2 is 5. These 2 is 5. So the minimum Hamming distance is 5. Right, between any pairs, they differ by at least 5 bits. So if you have a 4-bit error, let's say, it cannot bring you from one valid code to another valid code. So you can detect anything smaller than 4-bit error. Right? 1 bit, 2 bit, 3 bit, 4 bit, those are all detectable. If you want to do error correction, to make sure that it's getting, the erroneous number is very close to the original number rather than some other numbers. So you cannot go more than halfway between this Hamming distance of 5. So if you have a 2-bit error, right, let's say 00011 00000. Well, if I know 2-bit error at most has happened, I can bring it back to this all 0 number to make error correction. Right? Since 0000, the all 0 number is the nearest neighbor of that erroneous code. So again, based on the minimum Hamming distance, if the error has not reached halfway between the minimum Hamming distance, then you can correct it back to the original number by just figuring out which one is the nearest neighbor to that erroneous code on the receiving end. So that's everything for error detection and correction. We started with the motivational example of food truck and good truck, and then talk about 2 out of 5, which has its own invariant of 2 ones out of 5 numbers. And we also talked about parity code, right, adding 1 additional bit. And Hamming code is just adding parity bits for different message bits to allow us to differentiate those different scenarios. Right? And then we formalize the error correction and detection capability in terms of the minimum Hamming distance. And then you can use that to reason about Hamming code, to reason about parity code, or even reason about some arbitrarily defined code settings. Yeah. Any questions about error detection and correction? Yeah. One thing I want to just briefly mention one more time is, when people develop these codings, they have these 2 things in their mind. First, you need to figure out what is the type of error that I care about, right? And we're talking about bit flipping errors for binary numbers. Credit cards are talking about like 1-digit error and transposition of 2 digits. And depending on that error assumption, you need to develop different detection and correction capabilities, right? Bit flip is like a relatively simple fault model. So we can match that easily with this parity behavior, even and odd, etc. And secondly, we need to define a set of invalid and valid codes. And those kind of validity can be defined as some invariant properties, or they can be embedded as some external invariant properties, or they can be just defined as an arbitrary set of valid codes. Right? You have all these choices. All right. So with that said, we're going to move on to the next topic, Boolean algebra. I think this is what many people are waiting for. Boolean algebra is the thing that is actually related to circuit design. And the way this course structured is as follows. We talked about binary arithmetics. We talked about some of these coding. Right? We're gonna see eventually how to build the adder in a Boolean circuit, how to build that combinationally and sequentially, and finally, how to put many of these things that you learned, combinational design, sequential design together to construct a scalable and to realize complicated operations. Right, so now we're coming back to the thing that is more related to circuit design. Right. Boolean algebra is developed by a guy called George Boole, of course. Boolean algebra is his algebra. And this was proposed in the book of The Mathematical Analysis of Logic in 1847. That is like 100 years before the integrated circuits were born. Integrated circuits were born like in 1958. Transistors were born in like 1920s. And it's like 80 years, 100 years ahead of it. And when he developed the algebra, he's of course not talking about circuit because circuit was not even a thing. He was talking about general reasoning, right? To model anything that we can think about. For example, like you could say you can model these kind of things in Boolean algebra, like I like to eat Panda Express, and it's summer, so many of the dining halls are not open, and what should I do after this class since I haven't eaten anything? So these kind of things can be modeled using Boolean algebra. That's what he was trying to do, but that turns out to be a total failure. As you can see, modeling these kind of things in an equation, particularly a Boolean expression, 0 and 1s, or even if you generalize it a little bit, that can be very, very challenging. So he runs into a debate with Sir William Hamilton, who developed predicate or quantification logic. You have these symbols, there exist for all, and these are like the foundations of modern math, right? Like any of the proofs you do, whether you do it by implication or reduction or contradiction, you're essentially using these operators. So this predicate or quantification logic turns out to be more successful. But Boolean algebra, eventually, I'll tell you who realized that Boolean algebra can be used to design circuits a bit later. But Boolean algebra becomes the foundation of integrated circuits. And it also evolves into a much larger field of abstract algebra. We'll deal with things like group, set, lattices. And those are very important models for some of the newer computational technology. Quantum computing, privacy-preserving computing, multi-party computation, right? Those are the foundations, the mathematical foundation for many of the state-of-the-art computer science topics. All right. And when we apply Boolean algebra to switching circuits, this is what we're dealing with. We're dealing with gates. Gates is a small component that takes some 0 and 1 inputs and produce some 0 and 1 outputs. Right? Inverted is a way to do inversion. You go from 0 to 1, 1 to 0. Right? OR gate, well, you must have seen them when you do programming. Right? You use a plus operator, you use a dot operator. Right? Those are essentially OR operation and AND operation. Or produce a 1 when any of the input is 1, right? Or is true when any of the input is true. And produce a 1 when both of the inputs are 1s, right? True and true gives you a true. And XOR is the difference between the two inputs. XOR produces a 1 when the inputs differ. This is actually the exact same XOR as we saw from the error correction, right? When you have an odd number of 1s, output is a 1. But in the two input sense, it's just like comparing if they're the same or different. If they're different, output is a 1. Or if you have an odd number of 1s, output is 1. They're exactly the same for a two-input operator. We have more gates. There are some other gates that are also commonly used. These are just the previous gates with a small bubble after the gate symbol. And these are called inverted gates. Right? Small bubble, like small square, represents, small circle represents inversion. Essentially, the OR gate together with an inverter is a NOR gate, right? Not OR. AND gate with an inverter is called not AND. And all of these conditions will just be flipped. Right? OR gate produces a 1 in these 3 rows. NOR gate is the opposite. AND gate produces a 1 only in this condition. NAND gate is the opposite. Right? XNOR is the opposite of XOR. With that, we can actually build a very simple circuitry based on what we've learned. We have talked about binary addition, and those are the binary addition rules. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is too big to fit within the current bit. So sum is 0, carry is 1. So you can model it in a thing called truth table. truth table is a way to represent input-output relationship for Boolean circuits. It has some columns for all your inputs, some columns for all your outputs, and therefore just enumerate all the input combinations. With 2 inputs, you have 4 different conditions to be enumerated, 0001, 1011, and then I'm just converting this description, the mathematical description in binary, into the truth table. And after that, it's just a task of matching some of those columns, right, the output column of the truth table, with the gates that we have just seen. Sum is 1 when A and B are different, when there's an odd number of ones, and that's an XOR gate. Again, symbol is plus with a square around it. Sorry, a circle around it. Carry is 1 when A and B are both 1s, and that is an AND gate. Right? Both of them are true, output is true. And after that, you can convert that expression into the circuit diagram, right, using the symbols that we just saw. XOR symbol, AND symbol, and then you have 2 inputs going into these 2 different gates, producing 2 outputs. This is essentially what we'll be studying for the next 2 weeks. Going from the behavior description into a more formal modeling, into the Boolean expression, into circuit implementation, that is called the implementation process, a way to convert a high-level abstract description into a concrete circuit implementation. Going the other way, from the circuit diagram to recover the expression, and then rebuild the truth table, and then figure out what the circuit does, that's called analysis. And going the other way, it's called analysis or reverse engineering. Right? One side is engineering down, the other side is reverse engineering up. And then along the way, you can also, this is a very simple example, so there's not really a room for optimization, but in general, you can do a lot of optimization when you do the implementation. So those are the 3 learning objectives for the next 2 weeks. Implementation, going down, analysis, going up, and optimization, which is like a step along the implementation process. And in general, you can also convert a multi-level gate composition into a Boolean expression by just iteratively breaking it down. So here I'm putting 2 gates next to each other. You can go from this side to the other side and gradually construct the Boolean expression. So B of the inversion is B prime. A and B prime, you can show that as an expression, A dot B prime. And then that one plus C, that's the final Boolean expression. Right? Even for this slightly more complicated Boolean expression, you can break it down little by little from expression to circuitry, and also picking up these variables along the way to build a longer expression. And eventually at the output, that will be your output expression, right? The overall functionality of the circuit. And I have an exercise for you. I want you to build this overtaking system for an autonomous driving vehicle. And this system can be modeled as 3 things. This is your vehicle. And there's a vehicle ahead of you. And you need to check whether there's any vehicles on your left and on your right before you initiate the overtaking decision. Right? So this can be modeled as a 3 input, 2 output function. The 2 output would be, one output is for you to overtake on the left. The other output is for you to overtake on the right. You have this in truth table. Right? So could you try to model this behavior in a truth table? And I'll give you 2 minutes to work on this exercise. And then I'll help you start by just putting down the truth table on the side if I have any space. I'll put it on the board. I'll be running out of space on this slide. And then we can fill it out together in a few minutes. Right again. Right, this is a system behavior, 3 inputs, 2 outputs. So you have A, B, C as inputs. You have overtake left, overtake right as the outputs. And for a truth table, we always enumerate all the input conditions. For the people sitting on that side of the classroom, I would recommend you to move a little bit on this side if you cannot see the board. Can I see that? All right. yeah, I'll provide a bit more hint for you to get started. So let's say if both left and right are occupied, right, you can definitely not overtake. If there's a vehicle here and vehicle here, you just shouldn't overtake, right? So if it's 1-1, I want my overtaking control to be false, right? To not overtake. Yes, Michael.
Car A is going too slow. Can you knock it over? Or what is?
So if A is driving at a normal speed, we probably don't want to overtake. And if A is too slow, you would want to overtake if at least one side is empty, right? So you have some space to overtake. So if A is driving too slow, you can choose to overtake on the left or right, depending on which side is empty. Yes.
Wait, so essentially when A is 0, right? Like when the speed is normal, that means that we don't overtake.
That's right.
So if there's only 0 and 1s, that can only happen. We only like go to left or right only when A is 1. If A is 0, then it's 0 for both outputs.
Yeah, I think that makes sense.
Okay.
I think I was calling you Eric earlier. I'm sorry, Max.
Yeah, all good.
All right. You got it, Roland? Chung, you got it? No, that's I'm counting you. All right. So, anyone want to show us how they designed it on the board? Come on. Oh, I think he raised the hand first, so I'm gonna let him do it this time. Maybe next time for you.
So you said if you're going normal that we don't want to overtake it.
Mhm.
So would that just override everything?
Yes.
Okay.
Yeah, if the car is going normal, I think for safety reason we just don't overtake. Or more like for simplicity reason.
Then we have a left lane occupied.
Yeah.
Then we want to go right.
Wanna go right.
And we have a right lane occupied, so we want to go left.
Yes. But you see you have like 7 rows in the upper column. They're like shifted a little bit. So there are like 4 cases over here, and then yeah.
Then I can go both lanes if I want to. They're both.
That's a good question. Thank you. Let me just draw the connection. It's a bit tilted, right? So if the right lane is open, right? Left lane is taken, so we go right. Left is open, right is taken, we go left. 0-0, well, you have a choice, right? And that really depends on the system specification. So if this is the thing that makes the final decision, you better not send conflicting control signals to the control unit. Right? If that's the case, you probably want to, well, maybe prefer to overtake on the left. Generally, it's generally the overtaking lane, it's like the faster lane. And in many countries, overtaking on the right is not that legal. So you may say, well, if it's both lanes are open, I just choose to overtake on the left, and then put the non-0 over here. But if these signals are received by a separate module to make that final decision, it's okay you send in 1-1 to that module, and then the next module will handle the final decision, the final control input sent to the steering wheel. Right? So you have some choices over here, depending on the specification. Cool. All right, so that's our first exercise, right? To convert some description into the truth table, and eventually you can implement this using the gates that I showed you earlier. But coming back to a bit of formality, this is how Boolean algebra is defined. Boolean algebra is defined as 2 elements, 2 operations, and 2 identity elements. And a set of Boolean algebra needs to satisfy those axioms. So axioms are essentially what we define to be true, to be valid. Right? And whenever you see an AND gate and OR gate, these two together will form a Boolean algebra that allows you to manipulate the Boolean expressions according to these algebraic rules. We're going to deal with some larger Boolean expressions. And to be able to implement them and simplify them, we need to know what are some algebraic rules that are valid for these newly defined variables, 0 and 1s, in their own space. So one of them is commutativity. A plus B is equal to B plus A. You can shuffle the order of the 2 operands without changing the output. Right? And all of the gates that we saw earlier, they're symmetric. You can shuffle the input orders to the gates without changing the outputs. Identity is also quite straightforward. 0 plus true equals true, 0 plus false equals false. Right? Same goes for the AND. Complements, true plus false equals 1, true plus false equals true, true and false equals, true and false equals false. Right? All of them can be interpreted by just assigning this variable with 0 and 1 and then verify the correctness of both cases. Distributivity is a little bit complicated. Right? This one, the second distributivity rule, this is also true in, it's very hard for me to write while holding the tablet. That is also true in the ordinary algebra. Right? You distribute multiplication into addition. But the top one, that is something unique to Boolean algebra, and you have to pay attention to it. Right? This is sometimes when people just make mistakes. Right? There's something that is only true for Boolean algebra, but not in the ordinary algebra. And then I'm going to give you a better visualization of what is happening with those axioms. Again, these 2 operations together define Boolean algebra. And when you manipulate Boolean expressions, we want to use these 2 gates and then following those algebraic rules. AND gate, I'm just representing that in a 2-dimensional truth table. Same goes for the OR gate. And again, each of these gates has an identity element, the one that defines the identity axioms. So 0 plus anything gives you back that element. 0 plus 0 is 0, 0 plus 1 is 1. So we call 0 the identity element for the OR operation. Similarly, and any value gives you back that value. So 1 is the identity element for the AND gate. And many of these axioms can be visually seen from this 2-dimensional truth table. Commutativity is saying that it is like symmetric between the 2 input variables. When you change the order, you should get the same result. And that will translate into a symmetric table across the diagonal. Right? This one is x and y. This one is y and x. So they must be the same. So it's symmetric across the diagonal. Identity is saying that while you use the identity element to operate with any of the other input variables, you should get back those input variables. 1 and 0 gives you 0, 1 and 1 gives you 1. So you should have a row, and by that commutativity, also a column that is the same as your input variable, the header of the table. Right? There's a row of 0, 1, column of 0, 1. So 1 is the identity element for AND. A row of 0, 1, a column of 0, 1, same as the header. So 0 is the identity element for the OR gate. Thirdly, complement. Every element in Boolean algebra needs to have a complement. 0 complement is 1, 1 complement is 0. So 0 and 1, based on the complement theorem, they should go to 1, which is actually, 0 or 1 should give you a 1, which is the identity element of the opposite operation. This is a bit of formality, right? Conceptually, this is quite straightforward if you plug in zeros and ones. But formally speaking, they will add up to the identity element of the opposite operation. So similarly over here, 0 and 1 is a 0, right? True and false is a false. So false is actually the identity element of the other operation. And finally, distributivity has no good visualization because it involves like 3 variables. It's very hard to see that in this 2-variable table. Right? So what do? Well, we just learned this truth table. The truth table allows you to really evaluate any function. It's a little bit complicated, but you can do it. So to prove distributivity, you can just plug in those 3 variables into some Boolean expressions and then show those partial Boolean expression and the final Boolean expression on a truth table. And this eventually allows you to declare that this one, the left-hand side, is indeed equal to the right-hand side for all the input value combinations. So left-hand side and right-hand side are equivalent. Right? So distributivity is true for this kind of inordinary distributivity rule that is only valid in Boolean algebra. All right. So that's everything for today. To sum it up, we talked about error detection and correction. Right? Parity code 2 out of 5, Hamming codes. We analyze the impact of minimum Hamming distance, how to analyze the detection and correction capability using that minimum Hamming distance. And finally, I give you a very gentle introduction to Boolean algebra. And we're going to continue on that topic together with circuit design, analysis, and implementation in the coming week. Right? And there's a longer workbook for today. A little bit, both for today's lecture and also to give you a summary of what has happened for this full week. And then it's worth 5% of your total grade.